Imagine for a second a concept that sounds, well, straight out of a science fiction movie, flying a machine directly into the outer atmosphere of the sun. I mean, it sounds totally impossible, right? The sun is millions of kilometers away. It's this enormous, churning ball of plasma pumping out truly unimaginable heat and energy. Yet, we actually have a spacecraft doing exactly that. This explainer is all about NASA's Parker Solar Probe, which is on a mission to unlock the secrets of our star.
So what would happen if you sent a spacecraft directly toward the sun? Well, it's pretty much the ultimate test of engineering. As this tiny probe gets closer to that extreme high-contrast environment and actually enters the corona, the physics get a whole lot stranger and way more violent. Scientists designed this entire mission to find out exactly what happens in there and to finally unlock secrets that have been puzzling astronomers for literally decades. All right, part 1, Journey to our nearest star.
When the Parker Solar Probe launched back in 2018, its destination was obviously the sun. But, simply flying toward it isn't quite as easy as it sounds. See, Earth is moving around the sun at enormous speeds. So to actually fall toward the star, the spacecraft has to lose a massive amount of that sideways orbital energy. And instead of just firing some giant engine to fight gravity the whole way, the mission relies on this absolutely brilliant piece of orbital mechanics, repeated close encounters with Venus. Each flyby uses the planet's gravity to basically reshape the spacecraft's path. It bleeds off that sideways energy and lets it plunge closer and closer to our star.
Which brings us to part 2, the solar corona mystery.
Because getting to the sun is really only half the battle. Surviving its outer atmosphere, which is called the corona, is a whole different story. Now, the visible surface of the sun is obviously incredibly hot, but here's one of the strangest facts in astrophysics. The corona actually reaches temperatures far, far hotter than the surface itself. It totally defies basic intuition. I mean, think about it like this. If you walk away from a campfire, you naturally expect it to get cooler, not hotter.
And that brings up a really fundamental question. Why exactly does the corona get so hot? What exact mechanisms are transferring all that energy from the sun out into this outer layer? And how does that energy eventually create the solar wind that's constantly flowing through our entire solar system? Well, the Parker Solar Probe was built to find exactly that out.
Moving on to part 3, surviving the extreme heat.
Obviously, to get any of these answers, the spacecraft actually has to survive. And the solution they came up with is just an absolute marvel of engineering. It's a specially designed heat shield known as the thermal protection system. This shield keeps all those highly sensitive scientific instruments tucked safely behind it at normal operating temperatures. And it does this even while the sun-facing side is taking a brutal, punishing beating from extreme solar radiation. But actually, temperature isn't the only factor at play here. Space, as you know, is a vacuum. And because it's mostly empty, heat moves through space very differently than it does down here in Earth's atmosphere. So the spacecraft has to very carefully manage exactly how much solar energy is touching its instruments, and it has to precisely control exactly how that heat is dissipated out into the empty void.
Part 4, measuring an active star.
So instead of just studying the sun from a safe, comfortable distance, we're finally in there taking direct measurements. And the Parker Solar Probe doesn't just, take pictures. It carries highly specialized instruments specifically to measure invisible processes. It tracks particles, it records magnetic fields, and it studies electromagnetic waves. By capturing these invisible forces directly, every single measurement we get back adds a crucial piece to the puzzle of our star. And we really have to remember the reality of this environment. The probe isn't actually going to land on the sun because there's no solid surface waiting for it anyway. Instead, it just continuously slices through that increasingly extreme outer atmosphere at really incredible speeds. Right amidst all these sudden energy releases and violent conditions, closer to the sun than any spacecraft in history, it just keeps on collecting data.
Now, for part 5, protecting modern civilization.
So why does all of this actually matter to us back here on Earth? Well, because the sun is definitely not a static object. It is constantly releasing powerful eruptions of charged particles. And when intense solar activity comes crashing into Earth's space environment, the effects can be highly disruptive. These events can interfere with our satellites, disrupt global radio communications, blind our navigation systems, and in extreme cases, even overload our physical electrical grids.
So understanding the sun is quite literally about protecting the vital technology that modern civilization depends on every single day.
Earth is very much a part of this interactive solar system environment. Literally every time you use your GPS, communicate using a satellite, or even just rely on the electrical grid to turn on the lights in your home, you're living in a world that is directly influenced by our star. And Parker's data is what helps us understand that solar wind and those magnetic fields, which ultimately allows us to predict and properly prepare for dangerous space weather.
In the end, the Parker Solar Probe represents something much bigger than just a really cool spacecraft. It represents humanity sending a machine into one of the most extreme environments in our entire solar system just to understand the very star that makes life possible for us. And it survives not by somehow overpowering the sun, but by working right alongside the laws of physics. It uses planetary gravity to steer, a genius heat shield to survive, and delicate instruments to measure an environment that we humans could never safely enter. For the very first time in history, we are touching the sun. And as Parker flies deeper and deeper into the solar fire, it leaves us with one final awe-inspiring question to think about. Once we finally master the extreme physics of our own star, how much further into the universe is that knowledge going to take us?